Our objective over here is to determine the strength of electric field at point C due to an electric dipole whose length is 2a, a plus a 2a. We have a minus q charge at point A and plus q charge at point B. And the point C where we have to determine the strength of electric field is at a distance small r from the center of the dipole. Now, at point C, the electric field which will be made, it will be due to the minus q charge and also it will be due to the plus q charge. So, the electric field due to the minus q charge, say we determine it by EA. And since it's a vector quantity, we will determine it with the EA vector. So, this electric field EA will be 1 upon 4 pi epsilon naught Q upon the distance square. The distance square is R plus A. So it will be R plus A whole square. And we are taking the direction towards A as minus I cap. We are considering this as the negative x direction and the right direction as the positive x direction. So the electric field EA will be in this direction. Say this is EA, right? And the electric field at point B, electric field at point C due to charge at point B, we determine it with EB and it will be 1 upon 4 pi epsilon naught Q upon R minus A whole square. Now the distance between the B and C is R minus A, this distance. And the direction of this electric field will be in the positive x direction. So this will be the direction of EB. Now the net electric field at point C, it will be due to both the charges A as well as B. That is what we need to do. We just need to add both these quantities. So the electric field at C, say we determine it with E, and this will be equal to EA plus EB, which we can write as 1 upon 4 pi epsilon naught, and I can also take Q common. So inside the bracket I have 1 upon R minus A whole square minus 1 upon R plus A whole square. Now when I solve this, I can write this Q upon 4 pi epsilon naught. Now if you see this R square, when I do the subtraction of these two fractions, the R square and A square of both the denominators will cancel out, and in the numerator we'll get 2AR from here and 2AR from here. So in the numerator I'll get 4AR, and the denominator I can write it as R square minus A square whole square. Now we also know that the electric dipole moment P is Q times 2A. That is, the dipole moment is the charge multiplied by the distance between the two charges, and it's a vector quantity which is in the direction of minus Q towards plus Q. This will be the dipole moment vector. So I can write the same formula in terms of dipole moment as 2p upon 4 pi epsilon naught R square minus A square whole square. Now the dipoles which actually exist in nature are extremely small in size. So in practical scenario, we encounter a situation where this distance r is too big as compared to the size of the dipole. So when r becomes too big as compared to a, then what will happen if you just compare this r square and a square? Obviously r square would be too big as compared to a square, since r any which ways is too big as compared to a. So what we can do is we can neglect this a square from here. So when I neglect this a square from here, I get over here in the denominator r to the power 4. And in the numerator, sorry, I have missed out r. So here you will have the r also. So in the denominator, you will have r to the power 4. And in the numerator also, you have 1 r. So 1 r and r to the power 4 will get cancelled out. And you will get in the denominator r cube. So final result which you will get here is the strength of electric field E as 2p upon 4 pi epsilon naught r cube. And if I see the direction of the electric field, obviously it will be what? It will be in the direction of positive x direction. So the net electric field E which we will obtain over here will be in this direction. This will be the direction of electric field E. This is quite obvious because the strength of electric field EB would be bigger than the strength of the electric field EA, since B is closer to point C.